what is fair ordering? So in Helix we call it a fair consensus protocol, and by what sense do I mean fair? So let's give a quick overview of how blockchain works. We have users. Users issue transactions. Okay, they issue transactions to the miners, and then the miners choose transactions from their pool to include in the blockchain, to include in blocks which are appended to the chain of blocks, to the blockchain. And the order of these transactions is important. Of course, we always think of money, and the order of who paid who when is very important. So this whole mechanism is bound to manipulations by people who wants to advance their transactions, or other people who wants to hold other people's transactions. Somehow this mechanism should be dealt with in the protocol, and the way this is done in Bitcoin or Ethereum and in the current blockchains is by a fee mechanism for incentives. Basically how this works is each user attached to its transaction, it attaches a fee, and this fee is paid to the miner which will include this transaction in the blockchain. So if I'm a miner, I get a lot of many transactions, and I can choose arbitrarily, if I'm chosen to be the leader of this, to construct the next block in the blockchain, I can choose arbitrarily from the pool of transactions which transactions I will include in the blockchain. And the way I'm encouraged to do it is by people willing to pay me for entering their transactions to the blockchain. And since I want to make the best, maximal profit, I'm choosing the transactions which have the highest fees. This is supposed to guarantee fairness in the sense of the free market. If I want to pay more money, then my transactions will be included faster to the blockchain. However, this gives lots of power to those who have money, those who have computational power, and it has one major drawback for our setting. It's meant to serve as a blockchain infrastructure for mass consumer applications. So our customers are the applications, the companies who have applications, and they have users, and the users are the ones who are issuing transactions. And it's highly unreasonable to ask for the users to pay for their own transactions. It's highly improbable that you will have to pay fee to Facebook just to upload a single photo. This drawback led us to a different definition of fairness, which we call a fair ordering protocol. A fair ordering protocol is one in which each transaction has an equal probability of getting included as the next transaction in the chain. Put differently, if you're a node in the network and you can see all the transactions that were issued but not yet appended to the blockchain, and you want to ask yourself what is the transaction that will be included next in the blockchain. So in a fair ordering protocol, the best gamble you can make is simply sample uniformly at random a transaction from the set of all transactions that you see, and that will be your best bet. There is no one transaction that has a better chance of getting included in the blockchain. So let me say how this is done in Helix, and first let me give a quick outline of our network, which is roughly the same as I drew before. So Orbs, the Orbs network. So in the Orbs network, again, as in other blockchains, we have users. The users issue transactions. Let's use this for transactions. And we have here nodes. Node 1, node 2. We have n nodes. Node n. So the users issue transactions. I have a very small word. Okay, let me use this part. So what are the phases of the protocol? Users issue transactions. Okay, then the nodes get these transactions and they forward them to one another so everybody would know about all the transactions. So then nodes forward transactions. The third part is, okay, a leader is elected among all these nodes, leader election. So one leader, say node 2, is elected to be the leader of this round. Then this leader constructs a block. Leader constructs a block, and then it proposes it to the rest of the network. So node 2 is elected leader. It constructs a block from its own pool of transactions. Here we have transactions. It constructs a block. And then it proposes it to the rest of the network. And the job now of the other nodes in the network is to decide whether to accept or reject this node, this block. If you think of Bitcoin, so the nodes accept the block if they accept it as part of their chain and point to it in the next block. And in our setting, we don't have this probabilistic mechanism of how to accept a block. We simply reach a consensus among the nodes in the network about whether or not this block is accepted to the blockchain or not. So the fifth step is other nodes decide whether to accept or reject this proposed block. And to understand how we attain fairness in Helix, I'm going to elaborate a bit about these two phases, about the fourth and fifth parts, about the construction of the block, and about the validation procedure that is performed by the other nodes. An important thing that is apparent here, if you think about it a bit, is that the pools of transactions differ slightly. This is an important fact that we must address in this distributed setting. We have a distributed protocol. We have many computers, many servers, each of them getting transactions and forward these transactions together to the other nodes. And we cannot expect that at a single point in time, two nodes will have exactly the same list of transactions, because what happens if I'm on the internet and I happen to sit close to the person who issued the transaction, or maybe I issued the transactions, and of course this transaction is in my pool before it got to other pools. And this is sort of the problem with distributed protocols. And also we have regular network latency. What happens if something got stuck, something dropped, some packet didn't arrive? So it's really something that we have to assume. We will use the pools to construct blocks in a fair way. And to prove things mathematically, we need to model this accurately. And the model is pretty simple. So we do the probabilistic model for this. Model this by the following statement or assumption that a transaction, for any transaction which is in what we call the global pool, which was all transactions that were issued sometime, but were not appended to the blockchain. So for each transaction in the global pool, the probability of this transaction to lie in a certain pool of node I is exactly alpha. Okay, so alpha is a network parameter that we think of as quite large. Think of alpha greater than say 0.9. And this is the model we'll use. It's very simple. It's very intuitive. So let me say it again. Transaction that was issued by node J is in the pool of node I with probability, say, 0.95. Okay, and now I have to explain to you how the leader constructs its block. remember in Bitcoin, the protocol says to the miner, okay, choose freely which transactions to include in the block and in which order, and it takes the ones who gets the maximal profit for him. In our setting, it's as follows. Okay, so random is fair. First, let me take one step back and say the idea behind this construction. Think of a fair consensus protocol is one that we don't know which transactions would be included next in the blockchain. And the best idea that we could hope for is, okay, simply ask the leader to construct its block randomly. Simply take your pool, choose transactions randomly, order them randomly in the block, and propose it to the network. So the best, but unrealistic method is to tell the leader choose randomly. Okay, simply take your pool, look at your pool, choose randomly, propose it to the network. However, the problem is that from the outside to any other node wouldn't be able to tell the difference between a randomly constructed block and a deterministically, manipulatively constructed block. And this is a very simple idea. For example, if you ask me to give you a random number between 0 and 9, say, and then I tell you, okay, I chose 8, you have no way to tell if I chose this 8 because I like the number 8 and I maliciously chose it, or I really, I don't know, rolled the dice in my head and then what came out was 8 and I told you 8. So the whole thing with random constructions are that they are indistinguishable from one another. But fortunately, this problem was researched, and in the late 90s, people came up with the notion of verifiable random functions. And it deals exactly with this problem. How can I construct something that would look random, that would be random for most needs, but still other people would be able to verify that this was indeed constructed randomly and no manipulations were made. Standard way to construct such a function in the random oracle model is simply to use a hash function. So a cryptographic hash function is usually modeled as a random oracle. And let's see how we use it in Helix to construct a verifiable random function for the blocks. So let's again go back to the leader. Yeah, the leader of and this is the pool, PL for leader. And it has many transactions here. TXM, TX1. So what we ask the leader to do is to order its block according to the hash value of each transaction. And we ask the leader to simply hash its transactions and order the transactions according to their hash value. So we have here we have now TX I1, TX I2, TX IM, where the hash value of TX IJ is lower than the hash value of TX IJ plus 1. This is a very simple idea. Take your transactions, hash them, get a numeric value, and order your pool accordingly. And now we ask the leader to simply take the minimal B transactions and include them in its block. So the block would be exactly these transactions. Oh, better put like this, TX I1 to TX IB. This is the block. And let me just say that B, I consider it as the size of the block. So we think of a block as able to contain 1,000 transactions or 2,000 transactions, and the pool is usually much bigger than that. Maybe it's twice that, 10 times that. Okay, and this is how we ask the leader to construct its block. So I want to explain why this is random, and then I'll have to explain why this is verifiable. So it's random because if we treat H as a cryptographic hash function, with in the random oracle model, it simply outputs a random order of the transactions. And then, of course, it's random. So the randomness is guaranteed by the random oracle model. Now, how this is verifiable? First attempt is like the naive solution. Everybody has their own pool. Okay, we have Pi here for some node I, and it has transactions Tx and I. Yeah, I is a bad notation. Pk. Okay. So it can do the same procedure. Okay, hash your pool, get an ordered pool, take the first 1,000 transactions, construct a local block Bk, and then check whether or not this equals the block that was proposed by the leader. This would be okay, but it cannot work. All blocks would get rejected with this condition simply because we have differences between the pools. So if for some reason the first transaction here or here, first transaction here somehow didn't get to its pool because maybe it was issued very recently, so the blocks here won't be equal. Okay, so that's the naive solution, and it's clear that it doesn't work. The better solution would be, okay, so do this thing and check whether or not if they are equal, but if they are similar. Okay, so the condition should be, is Bk similar to Bl? If yes, then accept, otherwise reject. So now the key point here is how to define this thing, how to define similarity. And there is a trade-off here. If we impose a very strict similarity, say 100% similarity, and we ask equality here, then obviously many blocks would be rejected. On the other hand, if we allow very low similarity, then all blocks would get accepted, but we wouldn't be able to show randomness. So in this trade-off, liveness is simply how fast a protocol runs, how many blocks are appended to the blockchain each period of time. So in this randomness liveness trade-off, we chose the following. So one, a randomly constructed block, or let's say a correct block should be accepted with overwhelming probability. Under this constraint, maximize fairness. To achieve this, we tried several ways, and what we finally came up with was the approach coming from the field of statistical hypothesis testing. So I want to briefly introduce statistical hypothesis testing, and then see how we use their idea to formulate a condition for accepting or rejecting a block. Somebody comes to you with a statement, and you have to decide whether the statement is true or false. Okay, this is the setting. But in statistical hypothesis testing, the setting is you don't have the complete information about this problem, the statement, to decide whether or not this statement is true or false. You only have a partial data. You can think, if you think of it probabilistically, so you have a partial sample of the world, and then you try to analyze or to assess what's with as much certainty as you can, whether or not the statement is true or false. And what we did is to take this approach to formulate a statement that an honest leader is making when he's proposing a block. And then the other nodes use the ideas from my statistical hypothesis testing to decide whether or not this this statement of the leader is true or false. Namely, is the block he's constructing is constructed randomly or not. So we again have I remind you the pool of the leader, the ordered pool, okay? Ordered. Let's see, transactions here, and then it takes the first B to its block, okay? And look at this last transaction here, TX B, let's call it B without the indices from earlier. So we call this, okay, we can look at the hash of this transaction, the hash of the last transaction in the block. We call this, we define it to be the threshold of B, of the block. Okay, what do we mean by threshold? We mean that the following statement is done by the leader. If I'm an honest leader, then, well, first of all, out front you can see that since the blocks should be ordered according to the hash values, this is the highest hash value which appears in the block. And a correct leader, a leader who constructs the block in the way it's supposed to, is also saying that this is the highest, that in my pool, I don't have transactions with lower hash values. So let me write it precisely. Correct leader statement. Correct leader's statement. Is actually saying that the block it constructed is exactly the set of transactions in its pool with lower hash value than the threshold. So a correct leader is actually making this statement. Okay, and how our other leaders, our other nodes, to verify this statement. So notice two things. First, that once this block was introduced, was published, proposed by the leader, the last transaction is exposed as well, and the hash value is public. So this threshold is public. Everybody can know this, have access to this value, and then they can check. So validators, what can they check? They don't know. Validators don't have access to the pool of the leader. They don't know which transactions lie here, but they do have access to their own pool. That's the partial sample of the word that they have. They have access to their own pool, and they know. So let me just say, they have access to. So first the threshold value, and second to their own pool. Okay, and now what they know. And they know that each transaction which appears on their pool by our probabilistic model, they know that each transaction appears in their pool appears in another pool with probability alpha. So they know that Tx is in P, say I, should say that the probability of Tx to be in PL is alpha. And they also know what's the hash value of this transaction. You know this hash value. And they can check whether or not the hash value of this transaction is below or above this threshold. And if it's below the threshold, they know that this transaction is below the threshold, and with probability alpha, it's in this pool of the leader. So with probability alpha, it should appear in the block. That's the whole argument. So conclusion is, for any Tx in Pi such that the hash of this Tx is lower than the threshold, then the probability of Tx to be in the block, not only in the pool, but also in the block, is exactly alpha. So validators can actually check, based on this alpha, they can check whether or not they have, how many such transactions they have. the more transactions that they have which lie below the threshold and not in the block, the more likely it is that the leader made some manipulations and included transactions that were not meant to be included in the blockchain. And so if this number is high enough, they reject the block, and if not, they accept. So I won't exactly get into the details. You're welcome to read the Helix white paper. Towards the end, we actually give the formal proofs of how exactly which alpha, how many such transactions are allowed. But this is the main idea. Let me just conclude by saying that with this method, with the numbers that we get in the paper, we achieve very close to perfect randomness. I mean, if you want to have your block accepted with even probability 0.5 or 0.8, you would have to more or less construct the block this way, the way you're asked to. And if you do even 2% of the block is constructed in a malicious way, and if you include more than 2% of the transactions which are not supposed to be included in the block, then your block would probably not get accepted. And that's how we achieve this fairness, this very close to randomness protocol, to being a fair ordering protocol. Just to sum what I talked about. Yeah, so I presented the Helix ordering protocol. And then I talked about fees in other blockchains, fees in other blockchains and their drawbacks in our setting, in Orbs, and then gave a definition, drawbacks for Orbs, and then the solution, a fair ordering protocol, and 5, I explained how Helix is fair, is almost fair. Yeah, and that's it. You're welcome to view the white paper and the execution paper that's probably gonna be published soon.